Now let's move on to our last topic of today, pressure vessel under external loading. So as I told you, this problem considers a pressure vessel containing high pressure gas of 8 megapascal, and in addition to that there is twist loading. Okay, so under this combined loading of the internal high pressure gas and the torsion T, and let's consider the geometry like this. The thickness of this vessel is 12 millimeter, and the outer radius is 102 millimeter, and inner radius is 90 millimeter. And given these geometry, J, the polar moment of inertia is given as pi over 2 c0 fourth power minus ci fourth power. Okay, this is something we have learned in a few months ago. So what you can realize from this chapter is that we are combining all the knowledge we learned from the beginning of the ME231 lecture, and this is finally combining all the knowledge. Okay, so this will be the final chapter considering the maximum normal stress and maximum shearing stress, and compare those maximum normal stress and maximum shearing stress with the maximum allowable normal stress and allowable shear stress, and say whether the structure is reliable or not. After this chapter, we're gonna start the discussion on how to predict the deflection of the beam and how to use the energy method to predict the deflection. So yeah, this will be the final stage of the predicting maximum normal stress and maximum shearing stress, at least from the level of ME231. Okay, so let's combine these two loading. So if we consider this top surface, we have all component. Yes, sigma x, which is hoop stress, is PR over T, and sigma y, which is the longitudinal stress, is given as PR over 2T. Now we have even tau xy from this T. Tau xy is given as TC0 divided by J. Okay, so to answer this question, maximum normal and maximum shear stress, of course, instead of internal surface, outer surface is likely to have the maximum. And let's consider these. So sigma x and sigma y, after plug in the values 8 megapascal and these values, we obtain 60 megapascal and 30 megapascal for hoop stress and longitudinal stress. And about tau xy from 17 kilonewton meter and C0 and J value, here we obtain 25.9 megapascal. Now, given sigma x, sigma y, and tau xy, it's time to apply the Mohr circle. So, what you have to do is you have to first find the location where we're gonna likely to have maximum normal and shear stress from the intuition, as I found here at the top surface, as I did back in the shearing, the circular shaft under torsion and bending. From the intuition, we have to locate this position first. After locating the position, you do apply the Mohr circle at that specific position. So the average stress is given as 45 megapascal out of this, and radius of the Mohr circle, sigma x minus sigma average square plus tau square, it becomes 29.9 megapascal. So having obtained the sigma and r, and if you locate the Mohr circle, the x position, it will be sigma x and minus tau xy, and it will be 60 and minus 25.9, and y position will be sigma y and tau xy, it will be 30 and 25.9. So what you can realize here is that, and also the average is 45 and 0. So what you're going to realize is that we have 60 and x here, and we're gonna have y around here. And out of the in-plane analysis, what you're gonna get is the because average stress is larger than r, out of the in-plane analysis, we're gonna have two principal stress, that is both of them is larger than 0. Okay, so because two of the principal axes turns out to be positive value, in 3D analysis, we should expect that the maximum shearing stress should occur in 3D Mohr circle case. So the third principal axis should be, and third principal stress should be 0, because at the outer surface of this pressure vessel we don't have any loading, no more stress and no shear stress, so we have 0 as our final principal stress. After completing this 3D Mohr circle, we can obtain the maximum shearing stress out of a 3D Mohr circle from these value, and out of this 3D Mohr circle, if you add up average stress and radius, 45 plus 29.9, it becomes 74.9 megapascal, which is the maximum normal stress. And by comparing this maximum shearing stress and maximum normal stress with allowable stress of the material that consisting this material, then you can answer whether the structure is reliable or not under gas pressure of 8 megapascal and torsion of 17 kilonewton meter. Okay, so with this, we discussed about three different kind of complex loading problem and complex structure problem, and hopefully this chapter provide you an opportunity to recall all the analyses and all the discussions we have until now in ME 231 lectures. Okay.